Swayam Prabha. Digital India. Educated India.
Okay, so welcome to the next class. So essentially in the last class we ended by looking at statistics of various systems, be it classical, distinguishable, quantum indistinguishable, and on top of that quantum particles either being fermions and bosons, right. So essentially we saw that the statistics followed by any particles can be written in this way. So e raised to the power epsilon minus mu divided by kbt plus kappa, where we saw that if kappa is 0, this is Maxwell-Boltzmann statistics, which is applicable for distinguishable and classical particles. Okay, and in the case of kappa equals +1, this is Fermi-Dirac, and this is valid for indistinguishable and quantum particle, and provided that quantum particle is a fermion, right, with half integer spin. And also towards the also we saw that if kappa is -1, this is a Bose-Einstein statistics, and this is again for indistinguishable quantum, and it is valid for particles which can be treated as bosons, right, with integer spin, all right. And once we finished getting these results, we also basically used the Maxwell-Boltzmann statistics to basically derive the molecular speed distribution for an ideal gas, right. Ideal gas is a classical gas, right. So essentially what we used for the special case when kappa is 0, when the density of the system is very low, temperatures are very high, the particles are distinguishable and can be treated as classical because energy levels can be treated as continuous. In that case, if we apply this statistics, we can actually derive the molecular speed distribution for an ideal gas, and the result matched exactly with what we derived for the kinetic theory. And you should appreciate the power of this result, because now if you introduce this factor kappa in the denominator, either being +1 or -1, we can now in theory apply this to understand the physics of what's known as quantum particles, right, which is completely out of purview in the picture of classical physics, right. In classical mechanics or in classical picture, there is no concept of quantum particles, and just by the virtue of the special property of quantum particles, either obeying the Pauli's exclusion principle or not obeying the Pauli's exclusion principle, they become fermions and bosons. And now we are using this concept, we can now appropriately count the number of number of energy states that are available to the system, appropriately evaluate the partition function, and can apply these ideas to basically quantum systems, right. So, that is the power of the statistical, the theory of statistical physics, right. So, today what we are going to do is, we are going to basically evaluate specific or heat capacity of a diatomic molecule, all right. And I will first explain little bit about what are the experimental results that we know from some experiments performed upon the diatomic molecules, why they deviate from the classical picture, and how we can incorporate the effects of quantum mechanics, okay, to understand some of these experimental results, all right. So, essentially what we are going to do today is heat capacity of diatomic gases. Okay. So, so if you remember from several classes ago, so we derived what is known as equipartition theorem. So, where we basically saw that each degree of freedom has an associated energy which is given by half kBT, which is equal to half kBT, right. And we saw that if we have a monoatomic molecule, right. So, monoatomic molecule, it can basically just undergo translational motion either along x axis or y axis or along z axis, right. So, a monoatomic molecule has degree of freedom which is equal to 3, which corresponds to its translational modes. Right. So, therefore, its average kinetic energy, internal energy, right. So, its internal energy would be equal to 3 by 2 kBT, and correspondingly okay, and so this is per molecule. So, this is average kinetic energy of such a monoatomic gas per molecule, and if we want to calculate the heat capacity, that would be the total internal energy Na times U and its derivative with respect to T at constant volume, and you can very easily see that this will be 3 by 2 Na times Kb, which is equal to 3 by 2 R, right. So, and we can in fact we also saw that we can generalize this result to any system which has f number of degrees of freedom, right. So, therefore, heat capacity for a system with f degrees of freedom, that would be f by 2 times R, all right. So, this was the result that we got when we were looking at the equipartition theorem, all right. But now what we can do is we can generalize this little bit more, right. So, now consider that rather than being monoatomic, we are diatomic, right. So, say we have a diatomic gas where atom A, so where there are two atoms, atom A, and there is another atom which is atom B, okay. They are connected together with a bond, say in this case with a rigid bond, okay, and say this is x axis, this is y axis, and this is z axis, right. And now you can see that on top of them being able to translationally move in space. So, this particle, this diatomic molecule which has two different atoms like HCl or something like that, they can like translationally move in space, right, and they can do it in all three directions. But on top of that, these molecules can also exhibit what's known as rotational motion, right, because they can also store lot of energy in a rotational mode, right. So, one mode where they are rotating along y axis, other mode where they are rotating along x axis, and we are assuming that the rotation along z axis, due to this being its symmetry axis, that does not contribute to it. So, therefore, for a heterogeneous, okay, that is important, heterogeneous diatomic molecule, so its degrees of freedom corresponds to the following. So, it has, so for a translational motion, translation, so it can have 3 degrees of freedom. However, if we contribute the rotation as well, it has 2 additional degrees of freedom, right. And we basically imagine such a gas molecule to have the heat capacity to be 5/2 R, right, because it should have 5 degrees of freedom. But now let us see what do experiments show us, right. So if we typically perform an experiment on such a diatomic molecule, so this is what we see, all right. So in fact, it turns out this is not always true. There is a very strong dependence upon the temperature, right. So it turns out if we are working at very high temperature, so let us say this is 5/2 R, so this is CV axis, so say this is 3/2 R, okay. So it turns out if temperatures are very high, we indeed get 5/2 R as the heat capacity. However, at very low temperatures, the heat capacity is not 5/2, but it is just 3/2. And if we perform controlled experiments, it turns out there is a systematic gradual increase from 3/2 to 5/2. So it is like as if below certain critical temperature, the rotational degrees of freedom, they do not contribute to anything. However, that contribution slowly begins, starts contributing to the heat capacity, and it rises gradually before it saturates to a value of 5/2 as we expect from classical theory, right. So basically what I am saying is, so beyond certain temperature, let us call it T star. So this is what we predict from classical picture, okay. However, we can't really understand the gradual increase from 3/2 to 5/2 from classical picture, and now we have to use the concepts of quantum mechanics, all right. And let us see whether we can basically understand this result from our theoretical principles that we have developed so far, okay. All right. So, okay, so let us start. So essentially what's happening is, okay, so so basically what we have to do is we have to write down the partition function of this in this case, right. And we know that okay, so what is the contribution to the total energy of the molecule, right. So basically if we consider an ith molecule, so for an ith molecule, so its kinetic and its total energy of this ith molecule, that will have 2 contribution. The first contribution will come from the translational mode, and second contribution will come from the rotational mode, all right. And therefore the partition function, okay, so partition function, so partition function in this case, so ZD, where D stands for the diatomic molecule, so that would be sum over all energy states of e raised to the power minus beta epsilon I. So and this is for single molecule, right. So this is the partition function for the single molecule, which is e raised to the power minus beta I, and this sum is over all the energy states of this ith molecule, which include both translational as well as the rotational modes. all right. And now what we can do is we can basically substitute. So this is again energy states, sum over all energy states, e raised to the power minus beta times epsilon Tr plus epsilon rotation, right. So this is basically e raised to the power minus beta epsilon translation times e raised to the power minus beta epsilon rotation, okay. And basically we are going to make an assumption. So assuming energy contribution due to translational and rotational modes are independent of each other, okay, which essentially means the molecule can independently translate in space and it can independently rotate, right. So those two modes are not really coupled to each other. So there should be no correlation. So its translational kinetic energy and rotational kinetic energy should not be coupled to each other, all right. So if they remain independent, so we can basically just write our partition function to be the sum over product as product of two sums, right. So basically we can write it as e raised to the power minus beta epsilon translation times e raised to the power minus beta epsilon rotation, okay. And we can like now split it between the two partition functions. The first contribution comes from purely because from translation and second comes purely from rotation, okay. And now we can now write down the form of the rotational kinetic energy, right. So we can see that so the rotational kinetic energy, so rotational, so this is epsilon rotational, so that is basically equal to half times I times so if we just concentrate on this picture, so there is a mode in which the particle is rotating along x axis and there is a mode in which particle is rotating along y axis, right. So any rotation in 3 dimensions will be sum of these two terms, right. So this will be omega x squared plus omega y squared, all right. And here I is the moment of inertia along x and y axis, which is basically same for both the axes, right. So the molecule can rotate either like this or either like this. However, the rotation along z axis due to symmetry, due to this being a symmetry axis, we do not contribute, we do not consider that contribution, okay. And since we can write the angular momentum, okay. So since angular momentum J, right, angular momentum J is basically I times omega, right. So where basically omega is, so where omega square is omega x squared plus omega y squared, okay. So we can write down our epsilon rotation as J squared, right. So which is I squared omega squared divided by 2I, okay. So we can write it in terms of the angular momentum. But we know that from quantum mechanics, we know that the angular momentum of such a diatomic molecule, especially at very low temperatures, at very low energy states, it's not a continuous, it shows quantum, it has like discrete values, right. So from quantum mechanics, we know that the angular momentum J is quantized. So basically, which implies it has well defined discrete values, okay. and it turns out we know that j squared is essentially j times j plus 1 times h cross square, where j can be 0, 1, 2, so on, and this is known as rotational quantum number. Okay. And therefore, we can basically, if we substitute this back here, so we can write our epsilon rotation to be equal to j times j plus 1 times h squared, h cross squared divided by 2I. Okay. And what is h cross? So, h cross is essentially just h divided by 2 pi, and h is the Planck's constant. Okay. So, basically what we are saying is, so there are well defined energy levels corresponding to these j values, right. So, say this is j equal to 0, this is j equals to 1, j equals to 2, and so on, all right. And on top of that, we also know that for any given j, so for any given j, there are 2j plus 1 degenerate energy states. So, degenerate levels. Okay. So, for example, for j equal to 0, that is just the one level. For j equal 1, there will be 2, basically like total of 3 energy states. For j equals 2, there will be 1, 2, 3, 4, 5 energy states, right. So, the degeneracy for every j is basically 2j plus 1, all right. So, therefore, we can now put all this information back into the partition function, which is z rotational, right. So, we can write the z rotational, the partition function contribution because of rotational modes can be written as follows. So, z rotational basically becomes sigma j going to 0 to infinity, right, times 2j plus 1, which is the degeneracy, times exponential of minus j times j plus 1 h cross squared divided by 2I times kBt. Okay. So, basically I am basically substituting the lambda rotation, epsilon rotation here. So, this form of epsilon rotation here, considering that for every j there is 2j plus 1 degenerate values, degenerate levels, all right. And you can very easily see that here j is a number, right, it has no units. However, the quantity which is h cross squared divided by 2I kb, right, it has units of temperature, right, has units of temperature, and let us call this quantity as theta rot, and this has units of temperature. And now we can basically write down our z rotational, the partition function, as sigma j going from 0 to infinity times 2j plus 1 exponential of minus j into j plus 1 theta rot divided by t, and this is what we can write it, right. So, so basically this basically tells us okay, and this basically can be seen as some kind of effective temperature, right. So, some effective rotational temperature. And now we can basically see that what happens at low and high temperatures with respect to this newly defined quantity theta rotational, all right. So, let us look at the first case when the temperature is very high, right. So, case 1, when which is high temperature limit. okay. And high temperature means when temperature is much greater than this effective rotational temperature in the problem, all right. And what will happen is, so our temperature of the gas is so high that over that, so the basically so in this case, so the spacing between rotational energy levels becomes much smaller than the typical thermal energy, which is the kBT, right. And basically, and in this case you can imagine that we can assume the energy levels to be, so treat energy levels as continuous. So, essentially what we are doing is, our temperature is so high that the molecule can basically jump to very much higher energy levels, right. So, it has access to a lot of energy levels, and since temperature is so high, we can treat those energy levels not to be discrete but to be continuous, right. So, in which case we can basically modify the form of our rotational partition function, right. So, in this case we can basically replace the summation with the integral, all right, like this. So, this will go from 0 to infinity 2j plus 1, which is the degeneracy, right. So, 2j plus 1 and exponential of minus j into j plus 1 theta ROT divided by t, and there is a dj, right. So, dj corresponds to the basically small window of these quantum numbers, right. And now we basically have to evaluate this integral, right. So, one way to do that is basically to change variables, right. So, let us define u as a new variable which is equal to j times j plus 1 theta by t, right, in which case we can see that our du basically becomes, so this is j squared plus j. So, its derivative with respect to j will be 2j plus 1 and theta rho divided by t times dj, okay. And from here we can see that 2j plus 1 times dj is essentially t times theta ROT times du, okay. And we will basically substitute for 2j plus 1 times dj, which is t by theta ROT du here, and the limits of integral will remain from 0 to infinity, right. So, as j goes from 0 to infinity, u also goes from 0 to infinity, okay. So, therefore, our partition function gets modified to the following. So, zeta z ROT basically becomes 0 to infinity. So, t divided by theta ROT e raised to the power minus u, right, because we are calling u as this number times du, okay. And this is a straightforward integral to do. So, this is basically minus t by theta and e raised to the power minus u and evaluated from 0 to infinity, right. And you can see that this is basically minus 1. So, this basically becomes t divided by theta ROT, all right. But remember what is theta ROT, right. So, theta ROT we defined as the effective temperature whose value is h cross squared by 2I kb, right. So, if we replace that, so this basically becomes T divided by h cross squared divided by 2I kb, right. So, this basically becomes 2I kbt divided by h cross square, and this is the contribution to the partition function from the rotational degrees of freedom, all right. and now we can take the log. So, log of the partition function, that basically becomes log 2I kb by h cross squared plus log t. Okay. Okay. So, so essentially what now we have to do is, we again our idea is to now calculate the internal energy of the system and later use that internal energy to calculate the heat capacity, right. Okay. So, if you remember when we were doing canonical transitions, we saw that, so the average energy, average internal energy in a canonical ensemble is basically as follows. So, the average, so internal energy is minus del by del beta of log of z, right. So, here we have to replace this z, the partition function, with z rotational, and this you can very easily see that this can be written as minus del by del t of log z times del t by del beta, right. So, remember beta here is 1 divided by kbt, and if we, you can very easily check. So, del beta by del t is minus 1 by kbt squared, right. So, therefore, if I now substitute del t by del beta as negative kbt squared, okay. So, this just takes the form, so this just becomes, okay. So, minus sign gets cancelled. So, this is kbt squared times del log z by del t, right, and this is evaluated at constant volume and number of particles. And remember, this is for one molecule, for single molecule. Okay. But now, since we are interested in heat capacity, we can multiply this with the total number of particles, right. So, for 1 mole of gas, so for 1 mole of diatomic gas, it has Na number of particles, right, or molecules, where Na is the Avogadro's number, all right. So, therefore, the total energy contribution from the rotational degrees of freedom for 1 mole of gas would be Na times kb t squared times partial derivative of log of the partition function with respect to temperature at constant volume and number of particles, right. And since we have already written down our log of partition function in two convenient forms, two convenient terms, one without any contribution from temperature and the other which is only temperature, right. So, this is an easy thing to do. So, this becomes Na kbt squared times 1 by t. So, this is basically Na kb times t, okay. And remember, all this is true in the limit T is much greater than theta rotational, right, in which case we can treat the energy levels to be continuous and we can replace the partition function from a summation to an integral, where integral is evaluated over this small range of these quantum numbers j, right, all right. So, so therefore, we can now see that this is essentially, so Na times kb is R times T, which is the gas constant, right. So, therefore, therefore, okay, so for one molecule, so the contribution to its rotational kinetic energy comes out to be kbt, right, which is 2 times half kbt, right, and this is the result which is in accordance with equipartition theorem. Since there are 2 degrees of freedom associated with this rotational mode, so the energy contribution is 2 times half kBT, right. So, this is in accordance with equipartition theorem. And finally, now we can evaluate the heat capacity, right. So, heat capacity CV, that is del partial derivative of total internal energy with respect to temperature at constant volume by definition, right, and this basically just becomes R, right. So, therefore, at high temperatures the contribution to the heat capacity from the rotational degrees of freedom is R, right. So, therefore, the total heat capacity would be CV would be 3 by 2 R, which is the contribution from the translational mode, plus R, which is equal to 5 by 2 R. Okay. And this, like in the plot I showed, this indeed matches with the experiments where beyond certain critical temperature T star we get 5 by 2 R as the heat capacity. All right. So, now we can go to the other limit, right. So, this limit was where the temperature was much greater than theta ROT, right. So, now let us go to the other limit. So, case 2 is the low temperature limit. Okay. And again, when we say low temperatures, that means these temperature values are temperature is much smaller than theta ROT, right. And now we are saying that the temperature the energy contribution due to thermal due to temperature, the thermal energy contribution is much smaller than the typical spacing of energy levels, these quantized energy, discrete energy levels, right. And in this case we cannot really treat it as a continuous case. Okay. So, since we can't treat it as continuous energy level, so we just have to write down this the form of okay. So, maybe I can write little bit. So, so the typical or the spacing between rotational energy levels is much greater than kBT. So, temperature alone cannot populate higher energy levels, right. So, therefore, we expect these molecules to just stay in the lower energy levels, maybe in the ground state or little bit in the first excited state. All right. So, therefore, the partition function Z ROT, so that again by definition is j going from 0 to infinity 2j plus 1 exponential of minus j times j plus 1 theta divided by t. Okay. But now, since there are very few energy levels which gets populated, we can't really replace this summation with integral, right, the way we did before. So, we now have to basically expand this. So, for j equal to 0, this is 1. So, this basically becomes so for j equal to 0, exponential 0 is also 1. So, we have, so this is approximately equal to 1 plus for j equal 1 we have 3 e raised to the power minus 2 theta by t plus 5 e raised to the power minus 6 theta by t plus so on. Okay. And remember what is our aim, right? Our aim is again to evaluate the internal energy which is given as follows, and then use this value to evaluate the heat capacity. All right. So basically what we want is we want to evaluate and we want to evaluate u rotational, which is evaluate u rotation per molecule, which is kb times t squared times partial derivative of log of z rotational with respect to temperature while keeping the number of molecules and volume fixed. And this you can very easily see that this basically becomes kb times t squared divided by z rotational times del z rotational by del t. Okay. Now basically we have to evaluate this quantity, and z rotational is given by this. Now if I take derivative of this, so here, so del z ROT with respect to t basically just becomes, so 1 gives you 0, so this is so minus 6 times e raised to the power minus 2 theta ROT by t times negative of theta ROT by t squared plus okay, so maybe I can do it on the next page. Okay. So if we take derivative of this, okay, so basically there will be negative of theta ROT divided by t squared, which will be common in all these terms, and this minus 2 will get multiplied by 3 and minus 6 will get multiplied by 5. So therefore those two negatives will cancel out, and eventually what we will get is, okay, so from this equation we can see that partial derivative of the partition function with respect to temperature is basically theta ROT divided by t squared. So first term gives you 0, the second term gives you 6 times e raised to the power minus 2 theta ROT by t plus 30 times e raised to the power minus 6 theta ROT by t plus so on. Okay, and we are ignoring all higher order terms, right? So basically all these higher order terms are neglected because we are assuming that temperatures are much smaller than theta ROT. So there are most of the particles still occupy the ground state, and there might be few molecules which are in the first excited state, and all higher excited states they are mostly empty. Okay. So now if we plug this here, right, so if we plug this back here, here, so we can write, so u rotational per molecule is basically kb t squared times theta ROT by t squared, which comes from this, times so I can take 6 out, the factor 6 out, common factor 6. So this is minus 2 theta ROT by t plus 5 times e raised to the power minus 6 theta ROT by t plus all other higher order terms divided by the z, right, and z is 1 plus 3 times e raised to the power minus 2 theta ROT plus 5 e raised to the power minus 6 theta by t plus so on. Okay. Now we are going to make another assumption. So we assume that temperatures are very low. Okay. So therefore, so assuming e raised to the power minus 2 theta by t is much smaller than 1, right, and this term is basically 0. So all the higher order term, even the minus 6 theta ROT by t is almost equal to 0. Okay. If we only keep the first j equals 1 term in our solution, so we can write u ROT for 1 mole. Okay. So, let us do this for 1 mole now. So, it will get multiplied by Na. Okay. So, this becomes Na times Kb and T square gets cancelled out times theta ROT, and I am basically just going to ignore all these terms with respect to 1, and here only this term will survive, right. So, this becomes so there will be 6 here. Okay. So, 6 times Na times Kb times theta ROT times e raised to the power minus 2 theta ROT divided by T. Okay. And for basically this is for 1 mole of gas. Okay. All right. So, maybe I can write it again. So, therefore, u ROT, the final result that we have is 6 Na Kb theta e raised to the power minus 2 theta ROT divided by T. Okay. And so this is what we have, right. So, this is for 1 mole of gas. Okay. Again, our next step is to now take its derivative, partial derivative with respect to temperature to evaluate the heat capacity. So, now heat capacity at constant volume is partial derivative of u with respect to T at constant volume and number of particles. So, this can simply be written as 12 times Na times Kb theta ROT times okay. So, so basically this is minus 2 times 6 times this theta ROT times negative of theta ROT by T squared times e raised to the power minus 2 theta ROT by T. Okay. And this negative sign cancels out, and we have 12 Na Kb T squared e raised to the power minus 2 theta ROT divided by T. Okay. And I can just write this as R. So, this is 12 R theta ROT by T squared e raised to the power minus 2 theta ROT by T. Okay. And this is our CV. Okay. And if you want me to plot this, so we can see that here the CV clearly increases exponentially. Okay. So, there is a negative here. So, as I increase my temperature, the contribution of this exponential term goes away, right. So, basically it is increasing, right. So, it goes up and then it saturates, right. So, this is basically my CV, right. This is my temperature T, and it turns out beyond certain temperature. So, this will become basically equal to R. Okay. So, it turns out you can like actually check if we plug these numbers here. So, for T by theta ROT almost equal to 0.81, okay, we can see that CV is basically almost equal to 1.1 R. Okay. So, this is R, this is 1.1 R, okay, and this value basically corresponds to 0.81 theta ROT. Okay. So, it is a value where it maximizes, right, and it gives you a number which is almost equal to 1.1 R. But we already know that this is not correct, because this result comes from the extrapolation of the case where temperatures are much smaller than theta rotational, right. So we already know when temperature is very high, our result basically saturates to R, all right. But from here we can very easily see that for T going to 0, so if we put T equal to 0 here, Cv basically just becomes 0, right. So this is what that case is. So when temperatures are very small, almost equal to 0, there is no contribution to the heat capacity from the rotational mode, all right. But for very large T, right, so if we take T to be very high, we already know that specific heat contribution, the heat capacity contribution is R, all right. So now essentially what we are going to do is we are going to okay, so just to summarize what we have done. So we already know that as a function of temperature, so CV contribution due to translational degrees of freedom, so that is 3/2, right. So this is 3/2 R, and so this is just this is okay. So this is C. Okay, so this is CV, and the contribution this is CV from translational degrees of freedom, but the heat capacity at constant volume from rotational degrees of freedom. So that contribution first increases exponentially and then saturates to a value which is R, right, and this is again the temperature plot. And if we sum these two plots together, right, so we basically get the final answer, right. So the final result essentially looks like this. So the total heat capacity basically if you, so this is 0, right, and this is R. So if we sum these two together, we should expect a function which looks like this, right. So below certain temperature there will be no rotational degrees of freedom, right. So therefore we will get 3/2 R, but at very high temperatures we will see 5/2 R, right. So this is where the CV is 3/2 R plus 0, right. So when temperatures are very low, so you get 0, but here we get 3/2 R plus R, which is equal to 5/2 R. Okay, and our this formulation of basically evaluating the partition function over quantized energy states, that basically captures the experimental data, right, experimental observations quite nicely, right. So experiments showed that the heat capacity gradually increases from 3/2 R to 5/2 R, and from our theory we have basically figured out or evaluated that exact mathematical form of that gradual increase from 3/2 to 5/2 R. Okay. So therefore we can see that from the concepts of statistical physics that we have developed in this course, we can explain some of the experimental results which are impossible to do from the purview of the classical ideas. Alright, so this brings me to the end of this course, and I hope you enjoyed this course and this was beneficial for you. And the concept that we have developed in this course, they will be highly useful for various applied courses that you will probably learn in your curriculum, like solid state physics and मैं फिर से बोलूँगा थोड़ा, हाँ, या वो कट कर लेंगे, है ना. So basically this brings me to the end of this course, and I hope this course was beneficial for you, and you learned something, so you learned a lot of new concepts, and I urge you to solve as many exercise problems as you can following any of the textbooks. There are so many textbooks available which will definitely help you in grasping the contents of this course in a much firmer way, right, in a much clear way. And again, thank you so much for attending this course, and I wish you all the best for all your future endeavors. Thank you.